Okay. So we're starting a little bit early. Okay. Let's see if the chat is okay. Check the sound. Okay, I'm using a better resolution here. Check the sound. Okay. So it's a little bit of usual delay, so that sounds like it's fine. Okay, so today I would like to do some examples. I mentioned that I would do some of them, and somebody mentioned one of the examples by email. Okay, so oh yeah, so somebody mentioned that they would like to see an example of a rate of change problem, average rate of change. Okay. So this is from chapter 3 still. Okay, so hopefully the board will be more clear than before. It seemed to be fine before, but now it should be even better because I have a higher resolution, which YouTube requires me to make now. So I was able to adjust that. Okay, so an average rate of change problem. Something wrong with the stream house here. Okay, it says it should be okay. My viewers may be experiencing minor issues. Okay. Okay. It says high CPU usage detected. You may experience performance issues. Okay. Anyway, I'm putting up this the problems here. Okay, so rate of change. Okay, so we have some problems here that are from chapter... Okay, somebody just sent me a message. Trying to see the context here. Okay. Section 3.3 exercises, section exercises. All right. So it says, for the following exercises, find the average rate of change of each function on the interval specified for real numbers b or h in simplest form. Okay, so for example, the first one, number 5, gives us fx equals 4x squared minus 7 on 1b. X squared minus 7 on the interval 1b. Right? So this is the interval where 1 and b are included. So what you do then is you take the average rate of change is delta y over delta x, where you take this to be x1, this to be x2, okay? And then y1 is f of x1. Okay, so the picture is you have the graph like this, whatever it might look like. You have a point x1 here, and you look at the y coordinate y1, x2, you look at y2. So you just look up the value by going up, right? Going up to the graph, or down to the graph, wherever the graph is. Could be below the x-axis as well. And then you draw, you think of this line between the 2 points, and then you calculate the slope, delta y over delta x. So that's the average rate of change. And that's the meaning of the average rate of change of the function over that interval, is that it is the slope of the line that connects the beginning of the interval with the end of the interval. So you have to go, from this point x1 you get the y1, and from x2 you get y2, right? And then you take the difference of the y's divided by the difference of the x's, and that's the same as the slope of the line from one point to the other. So that drawing the straight line between them is like an approximation, if you like. It could be, but it's generally, even if the line is close to the graph, it's an approximation. But if it's not, then you could still take that as the average, the average rate of change of the graph between those 2 points. So this does depend on the 2 points, not just. Okay. So it's just a matter of plugging in the numbers here to this formula now, and what we get is, so 4x squared minus 5 for x1, that will be, just plug in the numbers, 4 times 1 squared minus 5 is 1 minus 1. And for the second, it's just, well, replace x by b. So 4x squared minus 4b squared minus 5. Replace x by b. Okay, so now take the y's and subtract this minus this. Second minus the first one. Note there's a negative sign. Two minus signs in the cancel, giving you a plus sign. And the bottom we get b minus 1. B minus 1. Okay, so now in these intervals, one helpful way to see how it works is if you plug in 1 and 1 plus h. Okay, so you just change b to 1 plus h. All right? If I take b to be 1 plus h, so it's the same x1 here as here, plus h. Okay, so I'm thinking, so delta x will then simplify to h. Now usually in these situations where you take y2 minus y1 and x2 minus x1, and you have a formula for y, you have a formula for this function like this, some sort of polynomial in x, what will happen is there will be a cancellation of terms when you take this difference in the numerator. And you'll be able to divide by h. There'll be an extra factor of h after the cancellation. The constant term will cancel, usually. And then you'll get an extra h, which will cancel in the denominator. Okay, so I actually I can look for the cancellation here too, because this is only different because you're replacing b by 1 plus h. So 1 plus h, this is just h. b minus 1 is just h. So let's see, what do I get? So I expect a cancellation, in other words. So I just have to look for it. So let's simplify the numerator. 4b squared minus 5 plus 1 is minus 4. Okay, if I get something different, then I won't get a cancellation. So it's important I get that constant term correct, b minus 1. Now we can see this is 4 times b squared minus 1 over b minus 1. And you can see now right away from this will have 2 factors. It's the difference of squares, so that will always be written as a sum times the difference. Okay, so you can see right away there's going to be this nice cancellation, and right, you just get 4 times b plus 1. Okay, so that's going to be the answer here. So it's a simple formula. What they're asking for is a simple formula for this average rate of change in terms of the numbers. The numbers will give you more numbers here, real numbers, and parameters. And the parameters should also appear there. Usually it will appear there. It might not in some cases. But you won't have to bring in any other parameters besides the ones given. Okay, so you can see the other expressions have, in the other problems, like for example 8 says evaluate kx equals 4x minus 2 on 3, interval 3, and 3 plus h. Okay, now before I get into that one, so that uses this kind of notation rather than this. Okay, so let's just see what happens if I do it this way. So what I was saying is that you should get cancellation of the constant term then in the numerator, and just you'll get an extra factor of h, which will cancel the h in the denominator. For sure, you'll get an h in the denominator, right? This way, because that's what the difference of the x2 minus x1 is. So we'll need an extra factor of h, and now it's a lot easier to spot sometimes than this factorization. So it might be better to do it that way. So try. So all we're doing is we're substituting for b. Instead of b, we'll substitute 1 plus h. Okay, they're just equivalent ways of writing the same thing, right? So then what happens here? Okay, so this becomes 1 plus h into the formula. So 1 plus h, we have to take 4 times that squared minus 5. Okay, so now a lot of the work will come into just evaluating this. 4, 1, right, let's just do reverse the order. H squared plus 2h plus 1 minus 5. So then we get 4h squared plus 8h plus 4 minus 5, which is 4h squared plus 8h minus 1. Okay, so now we have y2. So we plug that into here, and then we subtract the minus 1. That's the same as before. Now it comes from here. y1 is still minus 1, because x1 did not change, even in its, well, here it is changing the form of x2, not really the value. The form is written in a different way here, that's all. Okay, so I plug this in, 4h squared plus 8h minus 1. And I still have this minus 1. So again, now you can see again it becomes plus 1. Cancel the minus signs, and you get plus 1 here. And that cancels the minus 1. So what do I have left over? I have h in the denominator. Let's just officially replace that with h. And I have 4h squared plus 8h here divided by h. So now it's easier to factor and cancel the, I can factor the h out easily now. H times 4h plus 8 over h, that cancels. So I get 4h plus 8. Which I can write as 4h plus 2 and that is equal to, in terms of, if I substitute back to get b, so I have to take h and plug b minus 1 in there. I should get what I had before. Okay, it's just, and indeed I think that's what I got, right? Okay, I just erased it, but I believe that's what I had before. Okay, so this might be, doing it this way, so that you get a simple factor in the denominator, and then just look for that simple factor to be an extra factor. You just take it out of the brackets, use the distributive law, right? That might be an easier way to do this problem than to look for the factorization of something, something more complicated, to try to find the factor in the denominator. But usually these problems, okay, what should help you is that factor is there, whether it's h or b minus 1. And so you should go looking for it, and if you can't find it, then something must be wrong somewhere. So check your math. Check your signs especially, these, to watch the signs. Okay, so any problems with that? So if you have any questions, please, you can chat, you can write it on chat or send Skype or something. The Skype will give me a little beep or something, so that's also, it's a good way to inform me during the live chat, during the live lecture, if you're watching this. Otherwise, you can always email me about, with questions later. And again, if you email me about a question during the lecture that I make something, maybe I make a mistake in the lecture, you can just write the time so I can find it more quickly. And I can correct it in the chats as well, or in the comment section. Okay, so another example of this type might be, let's say, number 11. A of t is equal to 1 over t plus 4 on 9 plus h. So let's see how it works for that. Okay, well, if we look at these questions, they're not exactly in the order of increasing difficulty. So if I look at 7, that should be easier than number 5 because it's linear. It's a linear function. I'll just look at it quickly anyway. 7 says p of x is equal to (4x plus 3) on 2 and then 2 plus h. Okay, so it's written in this way. That will make it easier in general. So you take delta p now over delta x. So it's the same idea as before. This is x1, this is x2, and then p of x, p2 is p of x2. P1 is p of x1. Okay, so here the notation is, I'm using the notation of, no, instead of y, I'm using p, that's all. So it's a little bit, maybe I'm using the notation a little bit improperly here, but p can be this replacement for y, and it's also the name of the function. Okay, so often, I'm a physicist too, so sometimes physicists will do this. So it's a bit of a improper notation, but usually it's understandable. So you just have to remember the context. This is just like y, and this is a function p, so that doesn't get a subscript, whereas particular values of p will get a subscript. So those distinguish between the different kinds of p here. Over x2 minus x1. Okay, now substitute it in and you get 4 into 2 plus h plus 3 minus 4 times 2 plus 3 over x1 plus minus x2, which is h. Okay. Now we put it in, evaluate this. Remember the brackets and the minus sign, extra minus sign goes there. So 8 plus 4h plus 3 minus 8 minus 3. You can see easily cancellation here and here, divided by h, so we get 4. h's cancel, we get 4. Okay, so now this makes sense because that's just equal to the slope of this line. This is just going to give us a line, slope like this, 1, I forget what, let's see. 1, 2, 3, 1, 2, 3, 4. It starts here and it goes up to here. This is the p-axis, this is the x-axis. So I'm just replacing p by y, or y by p. So the slope of the line is constant because it's a straight line, and it's 4. And so that's what this will tell us in the case of a straight line. So that's consistent with the notions here of average rate of change is in some sense the generalization of the slope of a straight line. Let's try one of these. Sorry. Used all of these yet. Okay, so a more complicated example would be number 11. Number 11 has the function a of t is equal to 1 over t plus 4 on 9 plus h. Okay, so don't be put off by these variables. These just mean x. So t just is x. T is the x value, and you can think of a as now the y variable. Okay, so again I write change in a over change in t, and what that means is a2 minus a1 over t2 minus t1. In our case, t2 is this, t1 is this. We're just thinking of t as the x coordinate now. This notation is useful in describing motion. Position, usually we can think of this perhaps as position as a function of time. This might be actually acceleration as a function of time, which is physics. But when you include t as the independent variable, x is usually called the independent variable because you're allowed to freely vary that. And once you vary that, y is determined because it's a function of x. So t is an independent variable. It's just usually thought of physically as a time elapsed. And this other variable is then what it tells you is the variable, the way that this variable changes in time, or its behavior as a function of time. All right. So things move, the position changes as a function of time. Usually, you might have x as a function of t. X is the old y. The new x is now the old y, and this was the old x. All right, so you could even consider position along the x-axis as a function of time. So it looks something like this. The x-axis has been rotated, and any sort of graph like this. It has to be a function, right? Because at each time there's only, if you track one particle, right? If you track a single particle, which is a point, let's say, you get only you get a function of time. It's only one position for each time. Okay. So again, I'm using the y variable and the function notation. They're the same, but the x here means a function of t. Here x is the variable y. Usually they're equal. So you graph this equation, for example. That's the graph of x equals x of t. Okay, just so you understand the notation, what it means. It's like y is equal to f of x. Okay, so evaluating this then, you get a2 minus a1. Right, so let's just plug that in. So a2 is 1 over t, which is 9 plus h, t2 plus 4. 9 plus h plus 4. Minus 1 over 9 plus 4. And then here I get h. T2 minus T1 is just h. Okay, so how is this going to work? Well, we put the two fractions over the same, we express them as over the same denominator. The usual way you, excuse me, the way you simplify rational expressions is you put it over the same denominator. And then again, we should get an extra factor of h in the numerator, which we can then cancel. So let's see how it works. So this is 1 plus h plus 13, 1 over h plus 13, minus 1 over 13, all over h. So multiply by 13 and multiply by 13 here. So let's try that. Sorry, h plus 13. So that's one way to simplify this whole guy. So we multiply in the numerator and denominator by the same factor, and this is what we'll get, not changing anything else. Right, this is here still, and this is here still, and we just multiply by these two factors. And then we can now cancel the h plus 13 with this h plus 13 and this 13 with this 13. We have to do it to multiply this by the distributive law. So both factors will appear for this term and for this term. But then you get cancellation. So what you end up with in the first term is 13, simply. And what you end up with in the second term is minus h plus 13. Oops, 13. And here you get 3 factors. All right, now subtracting, I get 13 minus h minus 13. So I get a cancellation of my constant term again. And just get minus h there. And minus h will cancel with h and give me minus 1 in the numerator and 1 here. So I get minus 1 at the end over 13, h plus 13. Okay, so that's my average rate of change over this interval. The average rate of change of that function over this interval. We could check graphically, does that make sense? Well, we have a here, we have t here. We have a function that's going down, so x at t equals, yeah, how's this going to work? At t equals -4, I have, it's undefined. So 1, 2, 3, 4. Okay, so what this means is that I start with 1 over t, so that function that's the hyperbola, which lies totally in the first quadrant, and I shift that to the left. So this vertical line is my new asymptote. When I add 4, I shift to the left. So I'll have something like that. So it's t equals 0, I'll have 4. We'll go through 4 here. And on the other side, I'll get everything's still all shifted over, so I'll get this graph, the other branch of the hyperbola. Okay, and if I go up to 9 plus h, so this, what's happening over here doesn't matter too much for this problem. What matters is up here at 9, right, 9 and, oh sorry, the value of t should be 1 over 4, not 4. So if I go to 9, the value should be 1 over 13, even smaller. And if I go further to 9 plus h, let's say h is positive, then I'll get something even smaller, because the graph, you can see, is decreasing along this branch. Now if the graph is decreasing, what should the average rate of change be between these 2 points? Should it be positive or negative? Well, it can't be positive, because the graph's, if that were so, the graph would have to go up at some point, but it's always going down. So you can easily see that it should be negative. Okay, so, and it is. So that's, so the slope, average slope, if you like, is negative. That checks. Okay. It's a pretty good approximation to a straight line here already. So because this is always decreasing, the slope of that line should be pretty close to the expression that we have. And actually, you can see that there's a limit. If h goes to 0, that means this point gets closer and closer to this point. This is 9 plus h. This gets closer and closer to this, and so the straight line will get closer and closer to the curved part. All right, so it's looking like this if we blow it up. This point gets closer and closer, and anyway, that's something that you'll see more in calculus if you take a class in calculus like Math 130. That will be a typical situation, and you would take limits of as h goes to 0 to get a limiting slope, and that line will be tangent, and the final result will be called the derivative. So that's just a preview of derivatives. And not only will you learn about derivatives, but you'll also learn how to calculate them in an easier way than this. There are rules for calculating derivatives which make it a lot easier. Okay. So this is partly a prelude or a preview of that, but this is a kind of algebra that eventually leads into calculus. All right, and then you can estimate graphically. So number 16 or 17 says estimate the average rate of change of that graph from x equals 2 to x equals 5. 1, 2, Okay, we could do that one. Okay, also in physics is a good example that you'll have position as a function of time. Okay. So suppose you have an increasing position as a function of time. Let's say it's simply t squared. Okay, so you're parabola here. So you get 1 second gives you 1, let's say, meter. So this is time in seconds, this is x position in meters. Its position along the x-axis. The x-axis is now turned up this way. So the idea is you have a point particle and it starts at 0 at time t equals 0. Right? And then it starts moving to the right for an increasing x, and it kind of moves faster and faster in the positive x direction. So it goes up like this as time elapses. So at 1 second, x is already at 1 meter. At 2 seconds, x is at 2 meters. Meter is a unit for, m is the unit for meter, seconds is the unit for seconds. Okay, so and it keeps on going like that. So this is the interpretation of the variables now. So we have a particle moving along the x-axis. It's moving in a straight line, but this curve shows that its position is not uniformly increasing in time. Okay. If you want it to be uniformly increasing in time, then you should choose some a and b so that you have a linear function of time. Then it will be a like this, and then b will be the slope of this line. So this will be b over 1. Let's say that's 1 second elapsed time. I'm sorry, the other way around. B is here and A is here. So what is B? B is the starting position at time t equals 0. Okay. So it's the position along the x-axis where you start. And A will be what? Let's see, A will be the change, it's the rate of change of position with respect to time. So it's simply A t2, A times t2 minus A times t1 over t2 minus t1. And this factors out the A, you can factor out the A and just get A. So that's as usual as before. It's the slope of this line where x is a function of t. But what is the rate of change of position versus time? That's called the velocity. in general, you would have, if you write this expression, it will be the average velocity over that time interval. But in this case, that's equal to the instantaneous velocity. That's the velocity I get if I take the times closer and closer to each other. Here for a linear function, the average velocity is equal to the instantaneous velocity. Instantaneous velocity. Okay, for this graph, I wanted to do the simpler one first, so that's why I stopped doing this one and I just did this simple case first. Now the particle is moving along a straight line, but it's moving faster and faster. From 0 now. So x of 0 is still 0, x of 1 is 1, x of 2 is going to be 4 meters, and so on. Right? Just by plugging in the times into this formula. So now the rate of change of x with respect to time is going to change depending on the intervals chosen, or the endpoints of the interval chosen. So here we have x2 minus x1 over t2 minus t1, which is t2 squared minus t1 squared over t2 minus t1. And this is equal to, factor it, and you get t2 minus t1 times t2 plus t1. Okay, and then this will cancel with this, and we get t2, or simply t1 plus t2. So let's see how that works. If you take t1 to be 0, starting time, same as here, t2 to be 1, let's say, then this is the slope of the straight line connecting t1 equals 0 to t2 equals 1. At the respect, and you have to find the x1 and x2 as well. What's the slope of that line? Well, it's 1. It's at 1, 1, it goes to 0, so it's just 1. And what does it mean? 0 plus 1, it's what you get if you plug in 0 and 1 in here. So delta x over delta t is 1. So it's saying that the average rate of change over this time interval, the average speed of the particle, it's the same as the average speed now. Average speed is 1. So it's what you do when you go from point A to point B in a car, for example. If you want to calculate your average speed, you take the distance traveled, the total distance traveled from when you started to when you ended, and then you divide by the total time it took. So that's what I'm doing here. I'm changing my speed all the way, but I'm going faster and faster, but the average speed is just the total distance traveled, 1, minus the total time traveled, which is 1. So that's the average speed, or velocity, average velocity. Okay. Another example in physics. So these are physics examples, and okay, I teach these also in physics 120. This, but it's useful for understanding average rate of change here as well. Another example is if you get the instantaneous velocity. So instantaneous velocity is obtained by taking a point x1 and then x1 plus h, and then you let h go to 0 in the formulas. So in this case it will be what? T2 plus is T1 plus h. So I'll get 2T1 plus h. And then when I take that going to 0, that's going to give me 2T1. So I call that the instantaneous velocity because the interval is going to 0. So if I take that slope at that average speed, the slope of that straight line connecting the 2 points, and I take the points going closer and closer together, it's a limit, so you don't actually take them exactly the same. That would give you an undefined ratio. But in the limit, you think of this line as approaching this tangent line, which is giving you the slope of that tangent line gives you the instantaneous speed or velocity. Okay, and now this is what you would read on the car's speedometer. If you're driving, then the speedometer will tell you your instantaneous speed or velocity. Now if that changes, if you think of that as changing as a function of time, then so you'll get a graph like this. Then if you take the velocity at t2, okay, t2 v2, and then t1 v1. So now if you take the average rate of change of velocity with respect to time, that's going to be called the average acceleration. Okay, so in physics this average rate of change stuff becomes quite important because you have important physical variables which are directly defined in terms of the average rate of change of another physical quantity. So namely, you go from position versus time you can get average velocity from the graph by choosing 2 points. If you take one point going to the other, you'll then get instantaneous velocity with respect to time. Okay, so that's a notion that again that involves calculus. When you take this limit, that will be called the derivative. Okay, and then you can do the same to the instantaneous velocity now, thinking of it as a smooth function of time. And when you do that, you get the average rate of change is the average acceleration, which you call A. And then you can also get instantaneous acceleration. Okay, so instantaneous velocity is is like, in some sense, the limit as h goes to 0 of delta x over delta t. Okay? And the instantaneous acceleration is the limit as h goes to 0 of delta v over delta t. And then you sort of stop there. Okay, I mean, that's enough interesting physics for, you know, for basically lots, you know, most of classical mechanics, actually. So we stop there. At least it's good enough for a whole course. To find the rate of change of acceleration is not too physically important, but the acceleration is important because it has to do with force. Anyway, that's all physics. So this does lead to interesting, realistic, or physically important examples. But that's the topic. Those topics we'll cover in more detail in the course in physics. Okay. All right. So if you have any more questions on that, I can certainly do. Oh yeah, I was going to do this graphing problem just to show you how that works. So here you're given a graph of a function. It looks something like, let's see, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. Let's say 7. But it goes up to 8. And then we have 1, 2, 3, 4, 5, 6, 7 here. All right. So then it starts at 2, goes up to, at 1 it goes up to 5. There's a local maximum there, and then it goes down through 3 at 2. Okay, that's a bit more accurate. So it goes through 3 at this point, 2. And then at 3 it goes down to 1. And then it goes up to 7 at x equals 5. And down to 3 at x equals 7. And then back up. It seems like it continues going up after that. And here it goes down. Okay, so the question is, estimate the average rate of change from x equals 2 to x equals 5. So you have to find the average rate of change, you have to find, you're given the x values. So this will be x1, this will be x2. So you have to find the y values. So you just look them up using the graph. At x equals 2, you get 3 for y. So x1 equals 2, y1 equals 3. x2 is equal to 5. And y2 then you can see is equal to 7. Here. Okay. So you're looking at the these 2 points are the endpoints. So if you draw the straight line between them, it's just the slope of that straight line. So delta y over delta x. So y2 is 7 minus y1 is 3, x2 is 5 minus x1 is 2. So it's 4 over 3, which is in simplified form already. Okay, so you could write it like that. Estimate the average rate of change from x equals 2 to x equals 5. Okay, so that's what I get for that. All right, so hopefully that's enough examples for now involving rate of change problems. You can also do it from tables. Number 27, for example, is a numerical one. So again, you look at the change in the year. That's going to be the like the x variable. So number 27, let's say, on the next page, 207. Table 4 gives the population of a town in thousands from 2008 to 2008, 2000 to 2008. What was the average rate of change of population A between 2002 and 2004? So it goes up, or no, yeah, it goes down from 77. So it goes from 80 in 2003. Try that again. It goes from 83 in 2002 to 77 in 2004. So its population is decreasing in the town. And then it also asks what is the average rate of change between 2002 and 2006. So then it still goes down, but not as much because the population goes up a little bit, 78 by 2006. Okay, so the average rate of change is these are the y values. These are the y values, these are the x values. So you take delta y over delta x. Over t, well, it's population, so call this p, and this is time. Population is, the change in it is negative 6,000, right? Because this is a population measured in thousands. And divide by the time is 2 years. 2004 minus 2002, so that's just 2 years difference. So you get minus 3. And how do you interpret that? Well, you have to interpret it as thousands per year. So a decrease, average rate of change, average rate of, in this case, population growth is minus 3,000 per year over that time frame. Right, so you get the same result if you go down 3,000 the first year and then down another 3,000 in the second year. But in the middle, it doesn't quite go down 3,000, it goes only 2,000. But that's okay. It doesn't matter what the function is doing in between. So here it's going down and up. It could be going up and then down. That doesn't matter as long as the endpoints are fixed, and then the slope of the line between them is always the same. Okay, so average rate of change is not, it doesn't describe the function very accurately between the 2 points. Just what are the relationships between the position, the initial positions and the final positions, or the initial values of x and y and the final values of x and y. All right. So that's the average per year over 2 years. Over 4 years, from 2002 to 2006, it's 78 minus 83 over 2006 minus 83 is 4. Or 2006 minus 2002 is 4, plus 4. So again, it's minus. Here we get 5 over 4, which is minus 1 1/4. So it's gone down in its magnitude. That's because it went down and then up again. So you're decreasing the absolute value of the slope from where it was over here. But it's still negative, as you can see, because it was a decrease overall. Okay, so as time increases, as time is increasing, you'll get a positive delta t here. And depending on whether this is positive or negative, you'll get a positive or negative sign here. So if you decrease a population in that time, it doesn't matter how much it decreases, you'll always get a negative number for the average rate of change. So it'll be a negative slope for the straight line. It's going down like that. All right. Okay. Now the other example I wanted to do, I've spent a lot of time on these examples, but hopefully it will help to reinforce the concepts for you. I also wanted to discuss an example. I think also we're needing catch-up. We need catch-up time here so everybody's on the same page in terms of homework. And I haven't given all the homework yet for this chapter, or this chapter yet, so still trying to do that. Still would like to do that. I wanted to look at this example of a function which came up in the first homework involving absolute values. So this is a good illustration of how absolute value functions work, and in general how piecewise defined functions work. So remember, a piecewise defined function is so this will be an example of a piecewise defined function. A piecewise defined function is defined as using several continuous functions on different intervals. So y of x, or f of x, is equal to three different functions. Let's say x less than or equal to x1, x bigger than x1, not including less than or equal to x2, x2 less than x less than or equal to x3, etc. And then you can keep on going until you get up to an nth function. So you can split this up as many times as you like, and then n plus 1, I guess you need another function for the rest of the interval, x bigger than n, xn. So this would be the general situation for a piecewise defined function. And along each of these intervals you have some simple function, say linear, quadratic, or whatever. And you you're using this as a case-by-case definition. So not all these intervals are, there's no overlap in these intervals. Basically, you split the whole real line into the union of these intervals, and they're all mutually exclusive intervals. So their intersection of one interval with another one, including adjacent ones, is always empty. So an example that I wanted to talk about was this function that appeared, namely x minus 1 absolute value minus, so the absolute value of x minus 1 minus the absolute value of x plus 1. And remember, for this one, you were asked to evaluate at different points, including minus a. So f of minus a is, you plug in minus a in here, and minus a in here to start with. So these act as brackets for this expression. And I can simplify this a little bit because the absolute value does not depend on the overall sign of what's inside. Right? Because it's the distance of this quantity from the origin. So it doesn't matter if I have it over here or have it flipped over here, which is what you get by a minus sign. So absolute value of x is equal to absolute value of minus x. So I can simplify this by making them both positive. And this I can change both signs as well and get a minus 1. Okay, so now I want to see what this function looks like, because some people try to evaluate this. Okay, so if you try to evaluate this, you need to look at the cases. Okay, so a minus 1 is not always equal to a minus 1. The absolute value of a minus 1 is not always equal to a minus 1. It might be the negative of a minus 1. Okay, so let's get rid of this general one. So we'll write it in this form of a piecewise defined function. So call this new function g of a. It's f of minus a. And by the way, the new function is a reflection of the old function about the x-axis. Remember, that's how you got the reflection. So we can always get the original function back by flipping g of a. X is changed to a now. So a will be a variable. Okay, so what are the relevant points here? Where would this function change its definition? Well, if you remember, you can write absolute value of x as x if x is greater than or equal to 0, and minus x if x less than 0. Okay? Because I always have to end up with a positive value. If x is positive, then it stays the same. If x is negative, then I change the sign by adding an extra minus sign here. That will cancel the minus sign that x already has and give me a positive value. Okay, if I replace this with a plus 1, let's say, absolute value of that, then this is equal to, again, I keep the whole thing the same. If a plus 1 is greater than or equal to 0, that's the same as a greater than or equal to minus 1. And it becomes negative of a plus 1 if a plus 1 is less than 0, which is the same as a is less than minus 1. All right? And finally, this one is a minus 1. So using the same idea, if a is greater than or equal to 1, a minus a plus 1, just change both signs, get the negative, if a is less than 1. So this changes its simple expression in terms of a linear function here. This is not a linear function, because the graph is not a single straight line, it's two straight lines. But these separately are linear functions. Okay, and now the division points where you change the definition are at -1 for this one and +1. Okay, so I should choose those as the intervals. So I take a less than -1 for starters. Okay, so that will, in that case, a is less than -1, then the first function will be minus a plus 1. Minus applies to both terms if I expand the brackets. So that's what I get from this. And then I get minus, well, what does that evaluate to for a less than -1? Well, I'm in this case right here. A is less than -1, then a is certainly less than 1. And so I have to write that as minus this whole thing. Okay, and that's equal to what? That's minus a minus 1 plus a minus 1. So the a's cancel, and I get -2. Okay, so that's for a less than -1. What if a is between -1? So that's the next interval. I go from for a greater than -1 up to and possibly including +1. Actually, I put the equal sign with the -1. Okay. So they're it's sort of symmetrically described here. These intervals are symmetrically written. All right. So now, what changes? The only thing which changes, this will still be the same, but this one will change from this value to this one. So I get a plus 1 minus a plus 1. You can see I'll cancel and I'll get just 2a. Okay, now let's just erase this and give myself more room. The final interval is a bigger than or equal to 1. On that interval, a is certainly bigger than or equal to -1. So again, I'll use this expression for the first one. And I'll subtract, now I have to use the first expression for the second one as well. So I have to subtract that. After watching my signs, I get cancellation of the a's again, and now I end up with +2. So simplifying this, I've had to do a calculation just to show you what the functions are at each interval. But to rewrite this, I get -2 for a less than -1, 2a for -1 less than or equal to a less than 1, and +2 for 1 less than or equal to a. So let's see what that graph looks like for this, what the graph looks like. So I'm still thinking of a as the x value, so I plot that along the x-axis. Like that. So a is going along the x-axis, and my function g is on the y-axis, so I'll write it like that. Okay, so over here, these are three simple functions: 1, 2, -2, 1 plus 1 plus 2, plus 1 minus 1. So I start off here. So anything below a equals -1, here's -1, here's +1, -2, +2. Anything below, if a is less than -1, then the value of the function there is the constant -2. okay? For anything, in the third case, anything, if a is bigger than 1, any value of a which is bigger than 1, then the value of the function is constant, the constant plus 2. Now what happens at a, or sorry, between those two, the middle one? It's 2a, so that's the function, it's like 2x. It's the linear function with slope 2 passing through the origin. Okay. So that's like y equals 2x. It's just between those 2 points, so I have to cut it off. It doesn't go forever like that, and also have to cut off the function, the constant functions as well. Okay, so this is what my function looks like, g of a, or y equals g of a. Now what do you notice about this function? Well, all these x and y values over here, the x and y coordinates here are just the negative of the same corresponding points over here. So this point is the reflection through the origin of this point. So it looks symmetric. It has an odd symmetry. So it should be an odd function. How do you get an odd function? How do you check an odd function again? You just check if g of a, sorry, I'm talking about g now. G of a is minus g of a equal to g of minus a. Okay, I can't just take this minus sign out, because you have different meaning. This is not multiplication. I cannot just take the minus sign out every time. I have to check to see if this is true in the particular case I'm given. So if I plug in into the formula the minus sign, I get back f of a, right? Which if I evaluate that, that's a minus 1 minus a plus 1. Absolute value of a minus 1 minus the absolute value of a plus 1. And minus g of a, well, remember g of a was absolute value of a plus 1 minus the absolute value of a minus 1. So if I take a minus sign in front of all of that, I get this. And now I have minus a plus 1, and the bracket applies, it leaves the minus sign and it applies to this one, and it cancels and I get plus a minus 1 absolute value. And that's the same as this. Both terms are the same, just in a different order. So it's nothing but the commutative law that tells me that they're the same. Okay. So this is an odd function. And you can see that the origin, the odd function, is 0, as it usually is. If that point is in the domain, then we must get, if x equals 0 is in the domain, then y must be 0 for an odd function. So this is an odd function. Okay, and then g, or f of a, the original function, what does that look like? It's the reflection of g of a through about the a axis. So I take the whole graph and I flip it down like this. So what I should get then is, here's minus 1, here's plus 2. So now the minus 2 becomes plus 2, and the plus 2 becomes minus 2, those constant functions. This keeps on going, by the way. And then between, this graph, instead of plus 2a, becomes minus 2a, since I'm just changing the slope. The y-intercept stays the same. Okay, so it's 1, minus 1, 1, 2, minus 2. Okay, so that's how this function gets evaluated. You have to look at the three possible different intervals. Well, in this interval, a less than minus 1, it's just a constant minus 2. Right? And you could evaluate that for specific values. Oops. I could change also x. I can change x or a back into x. It's true for all a, and so it'll be true for all x as well. All real values of x. I change the a back to x, so then f of x is equal to x minus 1. So I'm back to my original form. All right, now this, if I plug in x equals minus 1, for example, then I'll get minus 2 inside the brackets here, and this will be plus 2 when I evaluate the absolute value. And minus 1 gives me 0 here. So indeed I get minus 2 starting at this point. Anything less than minus 1, so for example x equals minus 2, and I get plus 3 minus plus 1, which is 2 again. Alright, so just doing the evaluation, I'll see that I'll get a constant here. And likewise, if x is bigger than 1, I'll get a constant here, and it'll be minus 2. And anything in between, say 0, just try 0 for example, I get plus 1 minus plus 1 again, so I get 0. So that's at this point here. Okay, so just checking values, check a few values to verify if it makes sense. If the graph makes sense. So a similar function would be just change the minus sign in between the two terms, the two absolute value terms, into a plus sign. Okay, well then what happens? Well, you might expect this to be now an even function. And it actually will be an even function. So now you can verify this. You'll have at x equals minus 1 and x equals plus 1, you'll get a change in the slope. So you get 3 straight lines, and they'll be connected at these points minus 1 and 1. In other words, connected means that you don't have to lift your pen from the page to draw the lines. So it's continuous at these points. In other words, it's continuous. So here you will, between minus 1 and 1, this, for example, will give you 0. X equals 0 gives you 1 here, and this will also give you 1. So you get the constant value of 2 between those 2 points. How do I know it'll be a constant? It's because this factor will give a minus sign because it's less than 1, and this will have a positive sign because x plus 1 is bigger than 0. Here x minus 1 is less than 0. Because this is negative, this is positive, this x's will cancel, and I'll get a plus 1 plus 1, which is 2. So that verifies it's a constant there. Above it, it will be 2x. So it will be the straight line that would have gone through the origin, but it doesn't go there through the origin, it's just slope 2. So it starts here and continues on like this. There's nothing on the graph there. And the other one is minus 2x. Slope is minus 2. So you can verify by using the case by case, the 3 cases on the 3 intervals. Minus infinity to minus 1, minus 1 inclusive to plus 1 not inclusive, and then plus 1 inclusive to infinity. And you can verify that algebraically as well as you can see from the graph that it is in fact even, so that's another check. You could you could check that algebraically as well. So it's always helpful to check your answers by using a different method of verification, such as going from an algebraic, from the algebra to a graph. Okay. And these properties correspond. You should know how they correspond from the algebra to the graph. For even, to check it's even, you just check if f of minus x is equal to f of x. On the graph, you see that if you flip it over the y-axis, does it stay the same? And the answer here is, in this case, it's obvious it's yes. In this case, you have to check it, but it will also turn out to be true. Okay, so that's probably enough for now, and it's 9:30 in my time. So I'll continue next time with, I'll give you homework on the rest of the chapter here, and then I'll try to schedule a quiz for next week, so that hopefully you'll have enough time to work on the homework and get some feedback for that by next week. And thank you for those who have done the exercises that I requested. You just submitted the answers, that's fine, and the graphs are fine, and I'll check over those. I'll grade some of the problems, maybe not all of them, but I'll try to give you some feedback on those as well. All right, okay, so have a good day. Take care, and bye. Good office. Shabakush.